So experiment 5 in our modeling and analysis lab, isentropic flow analysis in 2D supersonic diffuser and supersonic nozzle. So from gas dynamics that we have studied in 6M, we know that how the flow behaves when the Mach numbers are changed. So when the Mach number is less than 1, the behavior of the flow over bodies or uh, internally, that is through passages, is different when compared to whenever the flow Mach number is greater than 1. Okay, and we know that when the flow is supersonic, that is when the Mach number is greater than 1, there will be compression of the gas when the flow happens over uh, converging bodies. Okay, for example, you can see a figure here. Okay, or they say blunt bodies, whatever. Okay, so the flow, the gas gets compressed when they flow over blunt bodies or some obstacles. But the opposite happens when the same supersonic flow happens over diverging bodies, that is over diverging passages. Okay, so supersonic flow over diverging passages, they tend to expand further. The Mach number increases further when the supersonic flow happens over diverging sections or diverging passages. So this is the phenomenon. This is a natural phenomenon. Okay, so you can see again flow through supersonic flow through diverging passage. The Mach number further increases. The flow expands. Okay. So with all that in mind, now we'll study, or we'll visualize. We have studied how the flow happens. Now we'll visualize whatever we have studied through ANSYS Fluent. We'll design a simple geometry, and we'll simulate a supersonic flow through that geometry. So the geometry, it's been specified that we have to use a diffuser and a nozzle. So we'll study the flow through diffuser and nozzle for a supersonic flow. Right? So from the gas dynamics theory, we know that whenever the flow is subsonic, I think we have discussed this many times. We'll go through again. It's not a problem. When the flow is subsonic, the duct, if it is converging, it will act as a nozzle. If the duct is diverging, it will act as a diffuser. Okay, but when the inlet flow is supersonic, if the duct is converging, okay, the duct will act as a diffuser. In the same supersonic inlet, if the duct is diverging, the duct will act as a supersonic nozzle. Okay, this very basic theory of ducts in gas dynamics. Right? So going to experiment 5, some calculations required for experiment 5 and obviously 4. So if you see, if we want, so we know from all the theory of gas dynamics that a supersonic diffuser should be converging. So this is the basic. We just roughly put a converging duct, and now after this we have to find the exact dimensions of the duct. Okay, for a very simple supersonic diffuser, we can take a straight walled supersonic diffuser. We can design a simple straight walled diffuser. Okay. The ideal condition is, so the inlet Mach number will be greater than 1. An ideal supersonic diffuser should decelerate the Mach number, and it should reach to Mach number 1. That is sonic Mach number. That is the condition at throat. Okay, you can design a diffuser which is about this length, where uh, Mach number, the exit Mach number may not be equal to the throat Mach number, that is 1. That is also right, but the exit Mach number will be still greater than 1. For a complete uh, diffuser, okay, for an efficient diffuser, the exit Mach number should be as low as possible. That is Mach number 1. 1 is the lowest possible Mach number which can be achieved through a supersonic diffuser. That's the critical value. That's the maximum. That's the lowest value a diffuser can achieve through the throat. You can't further decrease by through this particular duct. If you want to further decrease the Mach number, you have to change the cross section. That is, the area ratio has to be positive. That is, the duct has to diverge. Okay, it has to be this. It should become a subsonic diffuser. It has to diverge to further decrease the Mach number, to decrease the velocity. Right? Now, roughly we have put. Now we have to decide what we have to decide. We have to decide some inlet flow Mach number. Okay, and from that inlet flow Mach number, whatever we decide. For example, if you want the inlet flow Mach to be 2, Mach number 2. So for that particular Mach number 2, you have to go to the isentropic flow tables for Mach number 2, and you have to find all these ratios and find and compute all the flow values, the pressure, temperature, area, diameter, all those things you have to compute. So for experiment 4, I have written very detail in very detail. Okay, so choosing Mach number 0.4 for subsonic diffuser, the inlet Mach number should be subsonic flow. It is 0.4. I'm sorry, M is the exit Mach number in this case. Fine, and you compute all other values and you find the diameter, etc. So now what I'm going to do is, so last class we had designed a subsonic diffuser. Okay, the same geometry we are taking for a supersonic diffuser, but in inverted condition, inverted case. So only if you invert it, it will become a supersonic diffuser. Okay, so since the geometry is same, the area ratio has to be same. Okay, so what I'm doing is, instead of doing various geometries for experiment 4 and experiment 5, I'm taking the same geometry. So for the same geometry, our area ratio will be same. So for the same area ratio, I am finding the supersonic Mach number in the isentropic flow tables. So if you interpolate, okay, for the same area ratio, you will find the Mach number 1.93. Okay, it's like reverse engineering. First, we fixed a Mach number and found the area ratio in the starting for the experiment 4. Now we want the same geometry. For the same geometry, we want a different Mach number. That is any supersonic Mach number. So for this area ratio, the supersonic Mach number will be 1.93. Okay. Now all other values can be found out using the same table. For same area ratio, you will get all other ratios. Okay. So using all these pressure ratios, temperature ratios, now we have to fix some values. That is, we have to fix the total pressure. We have to assume some total pressure and total temperature. Okay, so I am by referring to some papers and by my own experience in nail, I have fixed the total pressure to be 2 bar and total temperature to be 300 Kelvin. Okay, so total pressure is nothing but it's the uh, pressure in the settling chamber. Before the test section, there will be a settling chamber. So that pressure is 2 bar. For example, I will show. So this is a settling chamber. P naught I have written here. Okay, so all the experimental setup for flow analysis gas dynamics will be like this. Initially, there will be a settling chamber, then a test section, then uh, some exhaust section. So in the settling chamber, the flow will be stagnant. There will be a valve before the test section. Okay, since there's a valve, the gases are settled in the settling chamber. So it will be the conditions will be stagnant conditions. So those stagnant conditions are these 2 bar and 300 Kelvin. For these, substituting these values in the ratios, you can find P. I have found P to be 0.2848 bar. Substituting T naught here, you can find T 172 Kelvin. Substituting this P in this ratio, you will get P star about 1 bar, and similarly T star. So what values do we need among these in our ANSYS fluent? Apply all these conditions in fluent and get the contours. So this is the duct, right? So we have the duct. In fluent, we have named this as inlet, outlet, and wall and symmetry, right? So inlet conditions are P. We have to put stagnation pressure, gauge total pressure, and supersonic or initial pressure is this P. We have to put these both values. And in thermal, we have to put total temperature 300 Kelvin. Only these three values we have to put in inlet conditions. Outlet conditions, we may have to put P star, that is this, and gauge or backflow total temperature. Again, total temperature will be constant, that is 300 Kelvin. So if you put these values, you will get the contours required. So now we have put these values, right? After computation, okay, you can find the remaining values. That is, we didn't put T, static temperature at the inlet. We didn't put static temperature at the exit. We didn't put Mach number. We didn't give Mach number input to the system. So whichever parameter you didn't entry in the setup of Fluent, later you can validate. So these values can be used for validation. So at the end, by finding these values in Fluent, if you get same values, then whatever you have done is perfect. I'll show how to, we'll see how to do. So this is what, it's a supersonic diffuser experiment 5. So experiment 5 supersonic diffuser is here. So you guys can see here, I have taken the same geometry used for experiment 4. Okay, including the mesh, same geometry. And you can see how I have connected. The subsonic nozzle is converging. This has to be connected to supersonic diffuser. And the subsonic diffuser has to be connected to supersonic nozzle, because the nozzle becomes diffuser when the Mach number crosses 1, and the diffuser becomes nozzle when the Mach number crosses 1. Do not connect subsonic diffuser to subsonic nozzle, or subsonic nozzle to supersonic diffuser. Okay. Now I have already done. What I will do is I will reset everything. Whatever inputs I have given, I will restart the setup. Same thing, we'll just say okay. I hope everything is properly audible and visible. So we know what to do in the starting. You go to in general scaling. You just specify the units you have used in geometry and meshing and just close. Don't click scale or unscale anything, just close. Now check your mesh and report your mesh. Since it's supersonic diffuser and it's a compressible flow, you have to use density based solver. And since you're using only half of the geometry, you have to use axisymmetry. And next you go to models. So in the flow models, use energy equation. So I have told, referring to some research papers, they have found that k omega SST is a suitable turbulence model for internal flows. Okay, now materials, you specify it as ideal gas and viscosity by Sutherland's equation. Close. Now go back to models. You will get another option when you change the air to ideal gas. You'll get compressibility effects. You just go back and click it. Now materials is done. Now boundary conditions, inlet. You make it pressure inlet. So what is the pressure that we have? Supersonic diffuser. So total pressure is 2 bar, and static pressure, we have inlet pressure is P. So don't get confused with P and P star. For a nozzle, it will be P star. You can see here. For diffuser, it is P. We have to be aware of P and P star always. P naught will be same everywhere. So P naught is 2 bar, P is 0.2848 bar. So gauge total pressure is P naught, total pressure 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2 bar, 0.2848 is it? Just keep my sheet. Okay, 0.2848 double zero 1, 2, 3, 4, 5. It's 2.8 bar. It's not 2.8. 1, 2, 3, 4, 5. It's 0.2848 bar. And temperature is 300 Kelvin, total temperature. You say okay. Now outlet, pressure outlet. It's static pressure, gauge pressure at the exit. So it is P star. We have 1.0587 bar, 105,870. 1, 2, 3, 4, 5. 1.0587 bar. Thermal 300. Say OK. Now here in operating conditions, you have to put it 0. That's all. Just check axis will be axis, wall will be wall. Now reference values compute from inlet. It's simply just check. Okay, velocity is supersonic. Next, solution initialization. Go for standard initialization. Again, compute from inlet and initialize. Check your case. So just telling me to use second order equations. I don't need that. I'll just initially give 500 iterations. So in the monitors, I didn't change anything. It was default. Continuity equation, the residual was 10 power minus 3, and rest all equations will be 10 power minus 6. So meanwhile, we can look into this. So design. So this is the design. I had done some rough design for experiment 4 I had shared. So in this I have done very clearly so that you can understand. So the steps for designing this, first you have to know the theory, how the shape looks. Okay. So for experiment 4 subsonic diffuser has to be diverging. Okay. For diverging section, roughly you just put, and the notations are star notations at the inlet and normal notations at the exit. Because for a subsonic diffuser, the flow velocity decreases, Mach number decreases. Okay, so Mach number decreases in the sense at the entry it should be close to 1 for a very good diffuser, subsonic diffuser. The Mach number should start from 1. That's the maximum Mach number a subsonic diffuser can operate at. 1, from 1 to lowering, decelerating the flow from 1 to 0. Okay, so exit Mach number you can choose whatever you want. I'm choosing zero point 0.4. For zero point 0.4 we get all these ratios. You compute all the other values by assuming I have assumed 2 bar everywhere. Okay, assuming we are doing the test in same lab, same experimental setup. So chamber pressure 2 bar, total pressure 300 Kelvin, and we have to assume one more thing here, the exit diameter. I'm taking 100 mm exit diameter. So you can choose any value. It's like sizing, it's like a scale. Whatever value you take D, the corresponding D star value can be obtained through area ratio. The ratio will be fixed on 0.59, and you can take any diameter value. You can take 10, you can take 1. It depends on your model, what scale you want to build your duct. So I've taken 100 mm. So for 100 mm, we have I am finding area pi d square by 4. Okay, and using this a in a star, a by a star, I am finding a star. I got this 4939 mm square. Using this value with pi d star square by 4, I'm finding d star. I got 79.3. I assumed it as 80 in geometry, drawing the geometry in Fluent. Okay. Now we can the duct can be of any length with same area ratio. So you can keep this left side diameter 40, sorry 80, and right side diameter 100, and you can elongate the duct to any length. So but we can't do that. Okay, so for that I told there's a page in gas turbines by V Ganeshan, page 485. You can refer to that, or else I'll get the pic later. Okay, so that particular study in that particular page says that the value I've chosen, L by H ratio. So you can see here, H is the smallest diameter, L is the length of the duct. So L by H ratio has to be around a range for the flow for not to be separated. So I've chosen L by H ratio 2. H is nothing but D star. Okay. So D star we know 80. So 80 into 2, 160. So L is 160. That's all. So you will get the geometry from these values. Draw the geometry mesh accordingly, and put these values. Put P naught. Okay, for the inlet you have to put P naught and P star here. So inlet P star this, and exit this value. The gauge pressure for pressure outlet, temperature everywhere 300, and you compute, you'll get the contours. Same design, same calculations, same pressure ratio, same Mach number, but the duct is inverted. It will behave as a nozzle, subsonic nozzle. So their exit Mach number was 0.4. For the nozzle entry Mach number, I've taken 0.4, and the other side parameters are star parameters, sonic parameters. D star, D, L, everything is same, meshing is same, even the parameters will be same, because M is same, you'll get same ratios, you have taken same total pressure, same total temperature, all other values will be same. Just the side will be reversed, and you'll get the same contours. I have written roughly how to use the setup. You can use this, and now here. Same Mach number 0.4, sorry, this is supersonic, right? Same geometry, 1.59 ratio, but different Mach number. We'll see what we got. Okay, it stopped somewhere. And you can see how the contours look like. So we are looking at static pressure contours. We'll put 50 levels. So this is how your supersonic diffuser will behave. So now for this, I wish to see Mach number. Now, if you want, you can view the other side of the axis also. Okay, I'll just cancel it. I don't want. Okay. So this is how your Mach number contours look like. So you can see here there's a shock wave produced. You can see the shock wave produced from the corner, which is same as the behavior is same as this. You're getting a shock wave, right? So the section is converging here, and you will get a shock wave. Same thing is happening. Section is converging here, and you'll get a shock wave. And both the shock waves meet at this particular point, and again they are uh, propagated through the duct. Okay, you can see how the Mach number is reduced over the shock wave. So it acts as a barrier, and you can see the red area here. It is Mach number 1.93, and you can see slightly orangish after the shock wave here. That is around. You can take this pointer. We can find So Mach number here is 1.9 almost. Here almost same 1.89. Just after the shock wave, we can see a drastic reduction in Mach number 1.6 and further decreasing 1.63 to 1.6, and there is a shock wave again. After the shock wave, the Mach number has reduced to 1.45. Okay, further reducing, there is an increase. It's 1.45 again. With the shock wave, 1.3, 1.3, and ultimately it has to come and land to Mach number 1. So if you do your iterations up to uh, convergence, so if you do for another 500 iterations, the accuracy will further increase. So now it is showing 1.16. So further, if you iterate, it will reduce to 1. Okay. So this is one way of seeing using this data pointer. Now you can go to reports. In reports, go to surface integrals, set up surface integrals, type area weighted. You're averaging on one particular plane cross section. So static pressure over inlet. So at the inlet, our static pressure is 0.2848. So we have input this value to the initially we have input this value to showing exactly how it is. At the exit also we had input static pressure. It was the value we had entered was 105,870 pascals. So it is almost close. But if you do some more iterations, we'll come to whatever the value you have entered. But why you got exactly 28480? It's because it's this initial value we have given compute reference value we have given compute from inlet. So that is fixed. So it will iterate, it will march, and it will find the exit value also. That's why the exit value shown here is not accurate. Now we'll see temperature, static temperature at outlet. We didn't input the static temperature. We had input total temperature. So we got static temperature 250, which is exactly correct. Okay, so if you see here, is this the diffuser? Yeah. So the diffuser we are doing static pressure T star at exit 250 Kelvin. So it's correct. So you just check the we didn't input the static temperature at inlet 2. So it is 172. It is 172 Kelvin at the inlet. That's correct. What else didn't we input? We can check velocity through Mach number at inlet. It is 1.929, almost 1.3 at the inlet. So we just check at the exit. It is almost 1. It's the average value. Okay, I think the experiment looks good, and whatever counters we are looking at are correct. So you can save the project like this. Another better way to save your project is export your case and data. So you can export your case and data. You select whichever folder you want. So I have done all my sorry, experiments here. So I'll name the case and data file as experiment 5. This is supersonic diffuser. Okay, your case is saved. Now, happily, you can go back And you can what have we done? Supersonic diffuser, we have done this. Now I'll erase whatever I've done here. It's not there already. Supersonic nozzle. So we can see how a supersonic nozzle is. It should be diverging, okay, and it will be very efficient if your inlet Mach number is sonic. That is the throat condition actually. That's why all your tables, the ratios are given with the star ratios. Okay, so exit Mach number, we have said we want exit Mach number to be 1.93 because we have same geometry, using same geometry. We want Mach number 1.93. So if you want Mach number 3, you change your geometry. You'll get a different area ratio. You just design that area ratio. You'll get Mach number 3 if you want. And accordingly, you compute all these values. Again, I have taken same test section. It is 2 bar 300 Kelvin. I found all the other values which are same as the supersonic diffuser, since the area ratio and Mach number are same. Apply all these conditions and get the counters. Okay, this setup is same for everything. For experiment 4 and 5, for both nozzle and diffuser, you can use same setup. Ideal gas, density based, axisymmetry, energy, k omega SST, compressibility effect, ideal gas, pressure inlet, all these things are same. Now supersonic nozzle. So do not assume how the flow will be in a supersonic flow. So, density based axisymmetry, scaling, check and report models, use energy equation, use k omega SST. See, you can see here there is no compressibility effect option here because the air is constant density. So now we have changed it to ideal gas, Sutherland. Now in the models you will get compressibility effect option. Materials is done, boundary conditions, change it to pressure inlet. So what do we have for pressure? Two bar, 2, 1, 2, 3, 4, 5, 2, 3, 4, 5, 2 bar. And inlet pressure should be P or P star. So for nozzle, it is P star is the inlet pressure. So what is P star? P star is 105870 pascals. You can cross check 1, 2, 3, 4, 5, 1.0587 bar. Temperature is 300 Kelvin. At the exit, it is P. So P is 28480. Cross check 1, 2, 3, 4, 5.2848 bar. Temperature is same. Operating conditions should be 0. Now you may get why the operating condition pressure is 0. That is because all the values we have taken for inlet and outlet computation, they are gauge values, gauge pressures. They are not absolute pressures. Absolute pressure, uh, it's a pressure that you measure uh, referencing with zero pressure. Okay, referencing with the ambient is uh, ambient having zero pressure and measuring pressure in a system, that is absolute pressure. Okay, here you're referencing with atmospheric pressure 1 bar. So you already have a reference pressure 1 bar. So you're already operating, that is a gauge pressure. You're already operating around atmospheric pressure 1. Okay, that is gauge pressure. So that is why the operating pressure is 0, because it's already included there. Reference values compute from inlet, initialize using standard initialization. So it will tell you to use second order. If you want to use second order, you go to solution methods. So you see here the turbulent kinetic energy and dissipation rate, they are first order, we can change them to second order. Every time you do some changes before this step, you have to initialize. Now, no recommendations to make. 500 iterations and compute. So using first order and second order, it's like your decimal value is increasing. Uh, instead of using dx by dy, you're using d square x by dy square. That's it. So you take this paper, you have to include all these calculations, all the theory, whatever I have written here. You just add them to your manual whenever you write your record. Write all this theory too, along with whatever I have given. Okay, and when you come to this step, you write in this way itself, but wherever we have some changes, you just incorporate all those changes there. The geometry also, completely delete this geometry and put the geometry that we have used. You put two sections. So section 1, supersonic diffuser, section 2, supersonic nozzle. Separately, do the calculation separately. Please do not show same calculations for both. They are wrong if you show in that way. Do separate calculation from starting. Okay, for both in the same fifth experiment. Okay? No need to put these meshing and all in your when you write your record. No need to put the meshing and counters and all. I mean, initially you just draw the geometry. Later on, you have to take printout and you have to stick in the record after performing, after doing somewhere. Okay, when you come to college or if you have a software, you can do at home. You can go out, you can take printout and you can stick. If you don't have any software, you can come to college. You have to do, you have to take printout and you have to stick. Okay. So I hope you guys will not confuse with all the changes. You have to look wherever there are changes and adjust the changes with these things. Okay. Wherever you get stuck while doing the experiment, you can very freely you can text me anytime. So if you give another 500 iterations, will converge. supersonic nozzle. It converges around 950 iterations, somewhere around that. But we're good to go. We can trust the contours. So I'll put increase the number of levels to 50. You have to increase the number of levels based on your computer speed. You can't simply increase. Okay, it has to compute that also, right? This is the pressure contour. I will view both the sides symmetry. Okay. So whatever you are seeing there, uh, it's an expansion wave. The yellow line that you are seeing is an expansion wave. It's not a shock wave. Okay. Even here, the blue lines slightly there some expansion happening there, some sharp expansion. That's the difference between a nozzle and a diffuser in supersonic flow. So in a nozzle, you'll find expansion waves. In a diffuser, you'll see shock waves. Okay. Again, having shock waves in a diffuser is a plus point. Okay, the shock waves they increase the pressure behind them. So that's what we want. Okay, having shock waves in diffuser is a plus point. I hope you have studied types of diffusers. We'll see later. Velocity, Mach number. Okay, so you can see how the Mach number is changing. So at the exit, we are almost getting 1.9, Mach number 1.9. That's what this particular nozzle is designed for. To get Mach number 1.9, we are getting, then it's good. So at the inlet, the Mach number is 1. You can see here. There are some expansions, some drama going on in the duct, and finally the drama ends and you get Mach number whatever you want. So this you can very quantitatively you can average particular surface and you can see. So at the inlet, static pressure is same whatever we have put. At the exit, static pressure what did we put? We put 0.2848, that is 28480 bar, sorry, pascals. We are getting this. Okay, some error. Once it is converged, you'll get exactly 28480 pascals. Now we can see velocity at the exit using Mach number. It's 1.8. Okay, once it is converged, you'll get 1.3. At the inlet, it is almost 1. You check temperature at inlet 250. Yes, it is 250. Static temperature at exit, it is 180, but what do we have? 172. Okay, it will come down. That's all. So this is how you visualize various contours. What else do you want to see? You can see turbulence, kinetic energy. There's no turbulence. Intensity. Due to some flow separation here, the boundary layer that we used to discuss in HD. Okay, the viscous effects, the boundary layer, there is some, the Reynolds number has changed there on the wall, causing some turbulence. And okay, that's a turbulence. And further understanding, we can again say this Okay, export case and data as some file and save somewhere. Now close this. We can go to post processing. So in post processing, we can see vectors and what do you say? The streamlines. Okay, so initially you get like this. So there won't be any contours. You just create contour. Location for the contour. Select whichever one. Which is the periodic one, which is this side. Pressure and see number of contours. Initially it is 11. Apply and see how it looks. So this is how it looks. Nozzle, right? I will put 50. Okay. So this is how we can see in the post process. So if you want to see the other side, we have to import another contour, same periodic location, pressure. We have given 50. We have to go to view. In view, we have to apply reflection or mirroring about which axis? X-axis. I'm sorry. So about plane X, Z, Z axis. You apply, you get both the sides. You can't get in one single contour. You have to create another contour for the other side. You have to click on both so that you see both. Okay. So if you want to change the parameters in contour one, double click on contour one. I will increase to 100. So that double click on 2. You have to keep both same. Okay. Now before going back, you reduce the counter number of contours and go back. I'll switch off. I want to see how the vectors look. So location on that particular surface, sampling equally spaced, the rest of vectors, number of points 100. So if 100 is very less, you can increase to 500, 1000. Okay. So same thing, if you want to see the other side also, create another vector, vector 2, and in view, you just mirror it. Okay. So this is how the flow is happening. The flow is good to see in the diffuser because there is a shock wave. You can see a change in the direction over the shock wave. Oh, I have already done it. Switch off streamline. Increase number to 50. Okay, you can see the pressure count. You can see how the shock wave looks. Okay, now further, if you want to see this velocity, if you want to see pressure, you can select pressure and see. That's how the pressure is. But the interesting thing is to see the vectors. So edit the vectors to 1000 numbers, the velocity vectors. We can see a slight change in the direction of the flow wherever there is shock. Okay, you can see here the flow, the direction is the arrows are pointing a little upward. Here from straight to a little bit downward. Okay, like that. And there is streamline too. Streamlines are also good to see. I will increase to 2000. Sorry. There were 25. Huh? I will increase to 100. Okay. So if you want, you can change the you can change the lines to tube. You can increase the numbers, but tubes will have this problem. Okay. You can see here how the directions change over the shock wave. Okay. That's all. So finally, to conclude this, what you have to understand is how the flow behaves over different shapes of objects in subsonic and supersonic flow. Okay, so we have used ducts for both for analyzing the flow, subsonic and supersonic flow. We have used ducts, that is diffuser and converging and diverging ducts. So how the flow, whether the flow accelerates or decelerates through the duct when the flow is subsonic and flow is supersonic, converging, diverging. At all conditions, all combinations we have seen. So all combinations is this itself. These four uh, cases, all these four cases we have studied in these two experiments. Subsonic, converging, diverging, supersonic, converging, diverging. Right? That's all. So if there's anything else to ask, we can ask now. And if you guys want to repeat any experiment in these two experiments, 4 and 5, any section in these two experiments, 4 and 5, you can ask me. There is experiment 6. If you guys want me to continue for experiment 6, we'll do experiment 6 now. It may take another half an hour. Okay.